Hello and welcome to a lecture on S parameters. I'm Steve Ellingson and this lecture was created on August 3rd, 2013. First, an outline of this lecture. First, I'll give an introduction to two-port theory, what it is and why it's important. I'll describe two ports and the way we parameterize them, that is in terms of Z, Y, and H parameters. Then I'll talk about S parameters. First we'll derive them. Then I'll tell you a little bit about why they're important and why we prefer these to the other types of parameters. And then some examples to familiarize yourself with how S parameters are used and what kind of values to expect. Three important cases, that of a series impedance, a shunt impedance, and a transmission line. And those three examples will get you started on the much broader class of S parameters and help you understand how to use those. The final topic will be discussion of methods for obtaining S parameters. So initially we'll kind of use an academic approach and derive them mathematically or from simple circuit analysis procedures. But I'll talk about other ways to do it, including measurements and other resources. Okay, first, two-port theory, what it is and why we're interested in it. Let's begin by considering why specifically we're interested in two-port theory. The electric circuits which comprise radios are typically pretty complex, consisting of hundreds or thousands of devices. Shown here as an example is a very simple radio receiver that I designed a few years ago. The analysis and design of the entire radio at the component level is technically possible, but you really wouldn't want to do this. It's not helpful and it's rarely done. Instead, what one typically does is to decompose this very complicated circuit into a set of smaller circuits which are easier to deal with, as shown here. So this is the decomposition of the radio into blocks that any radio engineer would recognize. Each block here is in fact a two-port device. What I mean by a two-port is a part of the circuit which performs a function that can be readily understood without detailed knowledge of the constituent circuitry. And I'll come up with a more precise definition of what we mean by two-port pretty soon, but that'll do for the moment. In this case, the two ports that I have described here are a relay, an amplifier, a digital step attenuator, a bandpass filter, another amplifier, another bandpass filter, and yet another amplifier. Let's first consider one of the filter two ports. The filter consists internally of 5 capacitors and 5 inductors, but from the perspective of someone considering the overall receiver, only the frequency response and the input and output impedances are really of specific interest. The filter schematic and the associated details are extraneous detail until the time comes to design or analyze that particular part of the circuit. The amplifier two-port highlighted here consists of an active device, in this case a monolithic microwave integrated circuit, which is abbreviated MMIC or sometimes spoken MIMIC. Plus some additional components which are needed to apply a direct current to the power of the device and additional components to isolate power supply from RF signals and so on. Again, from the perspective of someone considering the overall receiver, knowing the frequency response, in this case gain versus frequency, and the input and output impedance are all that is really necessary to know. Other details are certainly important, but only when it's necessary to design or analyze this particular part of the circuit. The decomposition of a complex design into two ports, in which the complex details can be hidden, is pretty important because without it, it would be difficult to understand modern radio systems, much less design them. Okay, so now let's be a little bit more formal about what we mean by a two-port. Here's a circuit theory perspective on this idea. As the name suggests, a two-port is a device consisting of two electrical ports. The behavior of the two-port is completely defined by the relationship between the voltages and the currents at the two ports, and they're identified here. The four quantities that we're concerned about are the voltage V1 and the current I1 at the first port, and the voltage of V sub 2 and the current I sub 2 at the second port. Please note carefully the conventions used for the orientation of current. Positive current flows into the port's positive terminal. So you see here I2 flows into the plus terminal of the two-port of port 2, and the current I1 flows into the terminal, the positive terminal defining V1 on the first port of the two-port. Assuming the two-port consists entirely of linear, time-invariant, and causal devices, or devices which can be reasonably well modeled as such, the port voltages and currents are all linearly related. The coefficients in these linear relationships can be identified in a number of ways, and that's what we now want to identify. The first scheme is z-parameters. You may have already encountered z-parameters. Z-parameters have units of ohms, and they can be interpreted as impedances because they relate voltages and currents. For example, Z21, this coefficient in the second equation, describes the effect of the current at port 1, that is I1, to V2. Now you have to be careful, because Z21 does not tell you V2 given I1, because V2 also depends on I2. And this is apparent from the equations. In other words, the relationship between V2 and the port currents depends on both Z21 and Z22. Sometimes it is convenient to describe a two-port in terms of admittances, that is, reciprocal impedances, as opposed to impedances. A good example is when two ports are connected in parallel. For example, parallel admittances add, whereas parallel impedances are fairly tedious to calculate. Thus, two ports are sometimes described in terms of y parameters, defined as shown here. And here are the defining equations. Y parameters have units of admittance, which is sometimes referred to as mhos, that is, ohm spelled backwards. And as you might expect, y parameters relate currents to voltages, whereas z parameters related voltages to currents. Otherwise, y parameters are quite similar to z parameters, and in fact, it's straightforward to convert back and forth between the two. Yet another scheme, which is sometimes used to describe two ports, are hybrid or H parameters. In this scheme, voltages and currents are described in terms of other voltages and currents. And the parameters have units of either impedance, these two coefficients have units of impedance, these two coefficients have units of impedance, or admittance, and the other coefficients are unitless. H12 and H21 are unitless. The reason this scheme is sometimes useful is because it turns out to be convenient and a natural way to describe some devices and circuits. An example of such a circuit is a transimpedance amplifier, which is a device which converts a signal defined in terms of its voltage into a signal which is defined in terms of its current. In other words, converts voltages to currents, or vice versa. Discussion of transimpedance amplifiers and other devices is a little bit out of the scope of this course, but it is a good idea to know that they exist and that they're used for applications including impedance isolation and radio to optical conversion. In total, there are at least 6 schemes for two-port parameterization which you should be aware of. We have just discussed Z, Y, and H parameters, which are in terms of the voltages and currents directly. There's another scheme, and this scheme is known as ABCD parameters. This is an important scheme, but it's so rarely used these days that I will not bother to describe it. You should be aware that there is such a scheme, though, since it was once very popular for the analysis of RF circuits, and you're likely to encounter it in older references. These days, S-parameters are by far the most important and commonly used scheme for the parameterization of two ports at radio frequencies. One reason for this is that S-parameters, in contrast to impedances and admittances and hybrid coefficients, are relatively easy to measure at radio frequencies. And I'll show you some examples in a moment. We'll focus primarily on this approach of S-parameters, and subsequent lectures will assume that you are proficient in this scheme. A disadvantage of S-parameters will turn out to be that the analysis of cascaded two ports is relatively difficult. Relatively difficult compared to some other schemes that we might have considered using. So this disadvantage is accommodated using T-parameters. So we'll discuss these as well, but in a later lecture. First, we'll figure out what S-parameters are all about, and then we'll discuss T-parameters later.